Okay. Hello, everyone. Welcome to episode 11 of Warsaw.ai. And then this meeting is dedicated to autonomous vehicles technology, self-driving cars, self-driving robots. So we'll be talking mostly about these topics and, of course, applications of AI in the domain of autonomous vehicles. And today we host three great speakers. Błażej Osiński from Lyft. He will give a lecture, data-driven approaches to self-driving. Then Rowan McAllister from Toyota Research Institute and formerly in Berkeley University will tell us that everything is connected and especially planning. And finally, Markus Wulfmeier from DeepMind will tell us about Hindsight of policy options, disentangling abstractions in the option framework. So I think we can start. So now I will just stop sharing my slides, and Błażej, you are the first speaker, so the Zoom is yours, and you can start sharing your slides. So thank you, Błażej, and thanks to all our speakers for accepting our invitations, and we hope that this will be very good and interesting meeting for all the participants. So enjoy.
Hello, welcome everybody, and thank you very much for inviting me to give the presentation. So, what I would like to talk about is self-driving, as probably everybody here. And self-driving is a very exciting idea. Like it will be probably less accidents, less time in traffic. Don't have to stand behind the wheel and so on. But somehow, like this future is kind of not there yet. Like so, I wanted to ask audience kind of like how many of you actually drove in autonomous vehicles by now? And I know like maybe you can answer in the chat and I will. So I see one, Rowan, so I know. So that's one in around like 30 people or two. Yeah. No, this is also Rowan. So it is just one and myself, so it's two. So I wouldn't say that's so many people. And on the other hand, for example, like do you know when there was like a first autonomous vehicles that was able to drive around 130 kilometers on a highway and doing this safely with disengagement less than like 100 miles, further than 100 miles from each other? And there's a very good answer. It was 1994 or around this time when Professor Dickman had his prototype. But I think that that's something that's kind of like not well known. So I'm happy that some of you in the audience have. However, so in 1994, like we had, a very good prototype, something that, was able to drive on the Autobahn with a huge speed. And by now in 2021, kind of, still like 2 people have driven autonomous vehicles. So, I mean, clearly there is some roadblocks on the way for us. So kind of what I think are the bigger one is how we apply machine learning to the problem. So if you take a look at the standard stack, so you have some sensor input like camera, lidars, and then you do perception to basically understand the situation around the vehicle. Then you do motion prediction, which is to say kind of what the other traffic participants will do. And finally, you do trajectory planning, which is kind of like what I should do in this situation. And like if you take a look at like the amount of ML used in these steps, it's decreasing, right? So it's almost 100% of ML in perception. Then it's a lot of machine learning motion prediction. But in trajectory planning, in many of the kind of deployments that we have at the moment, it's very limited. So it's like literally often just based on like rule-based systems and so on. So like not much machine learning there. And what's the limitation there is that if we have a rule-based system that we want to improve, we need to have more people writing more rules or like tuning it. And it does, and like people are like, it's a very hard process. So kind of if we could turn this into a machine learning problem, then we would be in a much better situation because we could let the data do the job. Like so, and the more the data we have, the better planner we do have. Okay, so how can you do planning? And so you can do it end-to-end. That's mean like from the sensory input directly to the steering and control of the throttle, or you can go meet-to-meet. I mean, this would be from some representation like bird eye view or like other representation of things around the car to some other representation of a trajectory, for example, going forward, which then can be controlled by a classical controller. And what are the potential approaches to do machine learning planning? So definitely, reinforcement learning would be probably a choice. Imitation learning or offline error is also a topic recently discussed. So why on-policy reinforcement learning is maybe not the easiest application for RL? Well, the reason is that in an approach like this, reinforcement learning is learning by a trial and error process, right? So definitely, you would probably not want to have autonomous vehicles trained in a trial and error process in the real world, because this will be a painful process. So what's an alternative, which we tried to do in this work, where I was still with DeepSys, and this was a collaboration with Volkswagen, was to do a sim-to-real approach. So we started to train a reinforcement learning agent in simulation, and we use Carla simulator, which is based on Unreal Engine. And the places where we wanted the car to drive, we modeled inside of the simulator. And then we could train, and in the simulator, we could make the car make mistakes. It's not such a big problem if it hits a simulated tree, right? It doesn't cause too much damage. But as you can see, there is a similarity between the simulation and reality, but it's not 100% accurate. So in order to make this transferable, a policy train inside of a simulator to the reality, what we have done is we make the simulator harder. We have introduced so-called domain randomization. So introduce things like noise, different weathers, different quality of image, also this random cutouts of these black patches. So we make it much harder for the model to learn to drive in the simulator. But thanks to this, it was kind of robust to all these perturbations. Thanks to this, it was also then possible to drive in the reality. So here is a recording of one of our better models, and you can see that it can drive nicely on this parking lot with following the curvature of the road and so on. However, these are the results of many models that we train. And then you can see that this is far from being perfect, right? So we would like to have all of the dots on the around 1.0, so no interventions. And even for the best model that we could train end to end, it's quite far from there. So also during the talk, what I would like to underline are things in which ways in which you could try to contribute, or you could run the experiments yourselves. So if you don't have a self-driving car that you could run the experiments, what you can try to do is instead improve the methods in simulation. So for example, you can use Carla simulator. One of the limitations that we found with Carla simulator is that the scenarios there were, there were not so many scenarios representing a lot of interactions with other car, or more realistic scenarios. So we wanted to improve on this situation, and we transferred data, this time from reality to simulation. So we took two data sets of moving agents. One is on the highway and the other one is on the roundabouts. And we moved them to simulation. So this way, actually, we have now a Carla simulator, and you can conduct a scenario that actually happened in the real world. So hopefully this will be a bit more interesting than just using standard Carla scenarios, which are purely artificial. So yeah, apparently the Carla simulator really likes the Coca-Cola trucks, because they put them a lot on the in this scenario. There is the other scenario for traffic roundabouts. So if you would be interested in running yourself some experiments, you can download the code and you can run the Carla real traffic scenarios. And what's also kind of interesting in the setup is, because we are using simulator for this, you can use things that you would not be able to do easily in the reality. For example, you could check what is the best sensory input for a model, right? Would you prefer to have 4 cameras, Tesla style, or would you prefer to actually have a camera and a LiDAR? Or maybe you even assume that you have a perfect perception module which can parse the situation around you into this privileged bird's eye view. Well, I mean, all these approaches have limitations, but I mean, like you can run experiments in simulation and compare them. Okay, so at this point, I would like to change gears a little bit. So this was mostly about simulation and about experiments in probably mostly end-to-end approach. So now I would like to move more towards the not using so much simulation and meet-to-meet approach. So I mean, this is work which is I can just talk about. I have not done it, but it's called Chauffeur, and that's a very interesting work already from 2015, when it was shown that using imitation learning and not much and some complications, you can actually train pretty good models of driving, right? You see the two GIFs here of an example driving when it can nicely stop on the stop sign and resume and so on, then follow curvature. It was actually also shown by the authors that it can drive in the real world, not only in their simulator, which looks all very promising. However, again, like this work somehow was not, I mean, there is not too much follow-up work on this. And probably one of the problems is that there were the code was not released and the dataset was not released. And it's not that easy to collect a dataset like this. So for this reason, at Lyft, Lyft decided, it was a few months before I joined, to actually open source a dataset which can help other people do experiments like this. So like, so the 1001 hour dataset was released, which contains trajectories around our office in Palo Alto. And there's a lot of data that you can use to basically train an model similar to Chauffeur. What is more, we have also released a code base called L5Kit. It's on GitHub now, that you can use to train a slightly simplified version of Chauffeur. And we support like prediction of other agents, and it supports also planning. That's actually planning for the agent. And it will actually also soon support simulation. So the simulation part is described in another work, which is called SimNet. So SimNet is using the hammer that we know, that is machine learning and data-driven approaches, to not only train a car that can drive nicely, but also to validate the car and validate the process. And like how you can validate an autonomous vehicle, you need to have a cheap way to simulate a situation around the car. And that's exactly what the SimNet does. So basically, what SimNet does is it takes like a location of a car, and then it can either sample possible locations of other agents around it, or take one that's recorded. And then it can, based on imitation learning of previously observed trajectories, it can predict the movement of other cars. And it can also, and it does it in a reactive way. So if one of the agents is controlled by our self-driving system, all the other cars will actually react and will, so like if that one goes slower, then the other one will also react. So here are some qualitative examples. And yeah, I mean, the quality of the pictures might be improved, and hopefully it will be in the future. But like, so these yellow boxes are the cars controlled by SimNet, and the red car is our self-driving vehicle, which is being evaluated. And I mean, you will, I hope you can agree with me that like this, that the movement of this yellow cars looks pretty reasonable. We also validated here our assumption that we are operating on, that more data means better models. And we have trained different SimNets with different amount of training data. And the more data we have, the average displacement error, which is a metric for us how close we are to a realistic behavior, is going down, right? So like, and you can imagine that if we collect like even bigger data set, like maybe 10,000 or like 1 million hours, then it will be, the error that we will be achieving will be even lower, hopefully. One important part of why SimNet is so important, that an alternative to it would be to just replay the movement of other agents as it has happened in the real world. However, it has then the limitation of generating many false positives. So suppose, take a look at the upper left image, right? So the red car ego is driving a little bit slower than it used to in the reality. And now, like, just replaying what the original car done in that case, I mean, this is causing a collision. And if you take a look now on the upper right, then we have an example where a SimNet agent is controlling the vehicle, and it's not causing this real collision, right? It's actually slowing down and taking into account that the model is driving slower. On the lower row, you can see a similar example when the car is like doing, the yellow car is doing a cut-in. And the reason why it's doing a cut-in in front of the ego vehicle is that it was the recorded behavior. But now the ego is in a different location, and it's only affecting the agent's operation when we are using SimNet. So that's the lower right. And of course, like, you don't necessarily need SimNet. An alternative would be to implement by hand rules how the other agents should move around. But again, this is a process that we would like to limit, the amount of things that you have to implement by hand. Another interesting examples, I think, what SimNet has learned, helped us to find out, is that problem called causal confusion. So a causal confusion is when we train an agent with imitation learnings, such as like Chauffeur, for example, or similar, and we see that it starts making decisions based on a different reason that we would hope for. And I mean, a classical example is that the car learns to slow down only when it's already slowing down. And I think that Rowan can tell you a bit more about this, maybe on the next presentation. And like here, like another example of a causal confusion that we have seen is of a car learning to start an intersection only when the car behind it, the chasing car, starts moving. Because kind of if we do it in the log replay style, so kind of not interactive, I mean, it's a very nice strategy, right? That start moving on the intersection only when the car behind you starts moving. However, if you replace this with a simulated agent, they will not start because, I mean, they know that the car in front of them have to start moving. And this way, we have actually like exposed another causal confusion of a model trained like ChauffeurNet. So, I mean, I'm not 100% sure if ChauffeurNet would show the same problem, but it's quite likely. So actually, it seems that I still have like 2 more minutes. So I will use my backup slide. So kind of like another, but this will be just for a minute. So another interesting work I think that we showed is that data is really the king. And like the more data we can collect, the more a behavior of a motion planner similar to ChauffeurNet will increase. And kind of what's also important, the quality of data is less important than the amount of that one. And this is shown in the graph here, is that like if we collect data with AV grade, like the highest quality LiDAR and so on, and if we collect data on the larger scale, but with much cheaper sensors, like for example, camera only, and based on the camera, we predict all the behavior of all the agents around. So this is already gives us a similar error. And if we combine the two, we get even better error. So this means that like instead of investing a lot of money in the very expensive hardware that you need to have an autonomous vehicles driving, you can actually have much cheaper resources much cheaper sensors put on a lot of cars and collect much more data, and this can give you even better result. Which for us is another indication that like the data-driven approaches might have a very good prospect in the autonomous vehicle world. So thank you very much for your attention. Now there will be time for questions. And if all of this sounds interesting, I also recommend two events at the next CVPR. So we are co-organizing a workshop on autonomous driving, perception, prediction, planning. And there will be also a tutorial on the new frontiers in data-driven autonomous driving, which will be talking about the topics I had today, but like with much more time and much more technical details. So thank you very much. And of course, this is hiring if you would like to work on these problems.
Okay, great. Thank you. Thank you very much, Błażej. Yeah, actually, there is a question in our chat from Jacek. Is your sim-to-real technique based purely on vision, or is it multimodal? So do you also use LiDAR, for example? And which reinforcement learning algorithms do you use for training in simulation?
So the first work I showed, this was using only camera. So it was only based on vision. And the training algorithm we used there was PPO. I mean, it was like a distributed version of PPO because like we had to collect quite a lot of data, actually like a few years of simulated experience in order to make them drive.
Mm-hmm. Okay. Yeah, there's another question from Krzysztof. What kind of simulator do you use at Lyft?
Well, I mean, so like we have an internal, I mean, we have a few simulators, but I mean, one that we use a lot is based on this SimNet, which is on this, and we will be using more and more. So we're using on the self-driving, on the data-driven approach.
Mm-hmm. Okay, so there's a question from Daniel. Are you saying Tesla might be right by their data-driven approach and resigning from LiDAR?
Well, I have not worked for Tesla, and I'm not sure what exactly technology they have inside. And I guess my comment here was more of the data that you can use for training, not so much the data that you will actually use for the real autonomous vehicle, right? I mean, so kind of like if a small percentage of your training data has some glitch or like didn't, notice an obstacle because of a perception problem, I mean, this will not be such a big problem. But like if you actually have the autonomous vehicle, which has a perception problem and does not notice an obstacle, I mean, this can be deadly serious, right? So I mean, I think that like having a LiDAR, which is you can have much more confidence of predicting all the obstacles around you during the evaluation, during actually moving in the autonomous mode, right? Mm-hmm. So, well, I mean, I'm not sure about the answer here, but I mean, I would be very cautious before, like, deploying a car without a LiDAR.
Okay, thanks. There is another question from Krzysztof. What do you think about NVIDIA options? Maybe Krzysztof. Yeah. Mm-hmm.
Do you mean options for the simulators?
Yeah, Krzysztof, maybe you can clarify. There's a question, Isaac. Mm-hmm.
I mean, yeah, I mean, so like we are operating on in meet-to-meet approach, and this means that we kind of like don't need a photorealistic simulator. Mm-hmm. For us, the most important part about the simulator is that it can realistically predict the behavior of the other agents. And what about physics? I mean, that's a good question. I mean, like we are basically trying to mimic the physics based on data, again and just predict based on kind of how do we see the cars behave. So I don't have experience with NVIDIA simulators, unfortunately.
Mm-hmm. All right. Do we have any more questions? It looks that we've already asked all the questions in our chat. All right, maybe there will be more questions later. So thank you, Błażej, once again. Thanks for a great presentation and answering all the questions. So I think we can start Rowan's presentation, maybe even 2-3 minutes earlier. Yeah.
Okay. I'll share screen. Can you?
Yes, we can see our slides.
Great, great. Okay,
yeah.
Ready to begin?
Yes, we can begin.
Okay, great. Well, yeah, thank you everyone for coming along. I wanted to talk today about this idea that everything is connected a little bit more. And one of the things that I'm interested in especially is planning. So what I mean by this is that often in autonomous vehicles, there is this decomposition that teams will use where they'll have maybe a perception team, a prediction team, a planning team, and maybe a control team. And this is done for a variety of reasons. Often the problem of autonomous driving is incredibly complex. So it's easy to break these things down into these manageable chunks as a divide and conquer type strategy. Other strategies involve more kind of end-to-end type approaches, but I wanted to talk about the modular approach in this talk. And so the question I wanted to pose to you is, like, is this pipeline complete? Where we've got a feed-forward representation, a feed-forward software pipeline from perception to then to try to understand the world, prediction to try to anticipate the world in the future, and then ego planning, and then finally following that plan. And I think some of the areas that I wanted to talk to you about today is how it doesn't necessarily have to be purely feed forward. There can be a lot of interesting kind of backwards loops as well, where, so especially planning here can help with prediction, and it can also help with perception and coming up with representations that are going to be useful for what they're going to be, what perception will be used for downstream. Okay, so the two papers I wanted to talk about was how planning helps prediction, and so this is a paper on what we call predictions conditioned on goals, and a second paper like how planning can help perception, which was resulted in a paper called Deep Bisimulation for Control. Okay, so the first one is involving settings where you've got multiple agents. And so we'll assume here that, say, the blue car is the ego vehicle, and here the orange car is maybe driven by a human. And we can collect a lot of data this way, where people are kind of driving around on these streets. The gray just represents buildings. And what we did was to expand on the work of imitative modeling, which basically just looks like this. It looks like normalizing flow autoregressive models. So here what we have is a series of states, this one for the ego vehicle, this one for maybe another human vehicle, and here we have latent variables. And everything about this network is deterministic. All of these neural networks that connect, that can make predictions from one state to the next. The only thing that is stochastic here is these latent variables. So these latent variables really represent, given the past joint state about where all agents are in the future, what might be the space of reasonable behaviors that each driver might take on a road. And so the one of the important aspects about coming up with a network like this is it needs to be multimodal. It needs to be able to predict distributions that maybe involve, turning to the right or going straight forward, but not in between, not something kind of diagonal that drives into a building. So this is something we can do with normalizing flows, and we can also compute exact likelihoods, which is helpful for planning. So yeah, initially, before we considered planning at all, this is what prediction would look like. So we've got kind of multiple agents, so say 5 different colors here. This is from the nuScenes dataset. And we've got triangles representing the past and squares representing the true futures, and circles predict the forecasted futures. And then this is what the scene looks like down here with the cameras. We actually only use the LiDAR. You can do surprisingly well just with LiDAR. And here what we've done is we've decomposed the LiDAR into everything that's road level or below, that's gray. So that's effectively the road. And everything red is above road level. And so this pre-processing trick kind of helps a lot. And then you can use your kind of convolutional neural networks to make sense of the scene. And effectively red is just labeling where all the obstacles are for our model. So basically these red points here is like this traffic light and this person, and then this big long red line here is like the building that we can see out here. And so, so moving around, this is kind of what it looks like. So we've got the ego vehicle here, and then we've got all of these LiDAR circles around, and then you can see in red basically everything that's above road level. And down here, this is what it looks like in the visual. I think they had 6 cameras, and we're just showing the front 3. So yeah, so this is it driving around both. I think this must be Singapore since they're driving on the left. I think, yeah. Okay, so that's fine. That's just prediction. But how can we combine this with planning, or how can we use planning to help prediction do a better job? It's a little bit of a confusing ask, but I'll show you what I mean. Okay, so say we have this forecasting setting here that we were just doing. So we've got 3 cars, and we're making joint predictions. So, maybe we predict this car here will go forward, this car here will go forward, and then this car is in an opposite lane going this way. So can we do something where we use the information that we have about the ego vehicle? So say it's an autonomous vehicle. We know that its route planner is telling us something, right? Like it's telling us where we want to go. We don't have to guess about our own intentions. We only really have to guess about the intentions of others. So can we use that knowledge that we have from, say, a route planner to better predict not only where we will go, but where other cars will go in response, given that it's an interactive setting? So, for example, if the route planner is telling us to go here, we can then condition our predictions on reaching that goal. And one of the interesting things about doing this in a multi-agent setting is you can then start to reason about what the effect of how your planning would affect your own predictions. Sorry, not only how it would affect your predictions, being car 1, the ego vehicle here, but it can also affect other vehicles. So if we start accelerating forwards, these are predictions from the model on the real data, even though I'm using cartoon cars here as an illustration. But so what has happened here is that if we predict that we'll accelerate forwards, we kind of anticipate that the car behind us, if they want to go as fast as possible, there's some predictions that are speeding up as well. The orange car doesn't really care, and that's kind of what we would expect. They're in the opposite lane. It doesn't matter if we're braking or speeding up because we're not impeding them in any way. The opposite also happens. So if we can condition our own prediction algorithm that we will come to a stop in the next few seconds, then what happens with the car behind us is what you would expect. So, if we're going to brake, we're pretty sure that the car behind us is also going to brake. And so we can use that information to come up with better predictions about how other vehicles will react to us. Okay, so that's all very interesting, but like, how did we do that? So before we would we would come up with predictions by just sampling these latent variables here. So these are the only sources of stochasticity. And then we would just feed them forward through the network as a purely predictive task. Okay, so we can kind of like think about the generating function like this. So we've got some autoregressive normalizing flow f. It's going to take a series of latents, a time series of latents here and here, but which really summarize like how agents typically react given the past. So this state here, conditioned on the past, this latent variable really represents the space of possible behaviors that are appropriate for that past. Okay, and so the planning objective following prior work on imitative modeling is to try to optimize the probability of a future state sequence conditioned on some goal being met. So this is kind of like pretending that if the route planner is giving us a particular waypoint it wants us to reach in, say, 8 seconds. We kind of pretend that, yes, we will definitely get there in 8 seconds, but we don't know how. And what we're going to try to do is building up a model of a density model about human interactive maneuvers. What we try to do is we then condition that density model on that goal being met. And we really try to ask the question, what if a human expert was driving this vehicle? What is the most likely path, or what is the most likely set of paths, given that this is probabilistic, that would get us from our current position that we know to our end position, which we're pretending we know. So we've got these boundary conditions. We just don't know how we would get from A to B just yet. But we try to do it by optimizing this object. But this object is currently a stochastic object, so we can't pass it to an atom optimizer just yet. Okay, so here is our goal, and that can be a bunch of things, but for sake of this talk, we'll just say it's a desired location. And just for numerical reasons, we'll use a log in front of the probability. We don't want to do this, but it kind of helps with the optimization. And then what we do is we do kind of classic Bayesian decision theory 101, where what we're going to do is we're going to start by integrating out all of the things that we cannot control. So here, again, the only sources of stochasticity is basically agent intent, like how they want to react to a particular situation conditioned on the past. So here, so we've got these sources of stochasticity here, which generates stochasticity in the output states, which is why we saw like multimodal predictions, even though this function f is deterministic and the context is deterministic. Okay, so standard Bayesian decision theory will say integrate out everything that you cannot control. And then what we're going to do is optimize over the things that we can control. So we see this in the Bellman equation as well. Like it will integrate out any transition stochasticities, and then it will try to optimize over the actions, over the things that it does have control, and then just continues to make backups in that way. Okay, so that is the best thing we can do. And the result of this is a set of latent variables that maximize this term, averaged with respect to the fact that we don't know what humans will do in the future. And then what we do is we put those latent variables back into the model. So this is a little bit unusual, but we're setting the latent variables. And we can set them because the meaning of the latent variables was the space of plausible behaviors that any vehicle might take. But when we're in control of the ego vehicle, we get to decide what kind of behavior we want to take in a particular situation. So we do get to set our own latent variables, but we do not get to set the latent variables for other drivers on the road because we are inherently uncertain about their intent. it'd be nice if we could control them for our own planning ease, but we can't. So, so this is what it looks like. We can now condition on these latent variables, and they're now observed. So I've kind of filled them in here. And then this is that cause and effect that we saw before. So if we set this value here, that's going to affect our state. So this is a state one time step in the future, and that will in turn affect the future human states. Now, the future human states are, they themselves are not certain. They're still a function of other things that the human might do, but the uncertainty will start to collapse. And you know, we could see that when we stopped, sure, there was still a probability that the car behind us might keep moving a bit, but we're pretty sure that they would stop. And then the rest of the mechanics here is really to just put these latent variables in here, sample for the humans that we can't control, and then we get these predictions conditioned on our goal. So this was all a process of taking into account this object here, the goal. And then this is just imitative modeling decomposition, where we treat this as a posterior and break it down into a prior term, a goal likelihood term, and a normalization term that cancels out because of it's not a function of the argmax latence here. And so we're just left with this multi-agent prior and a goal likelihood. And this is really just saying, can you stick to the manifold of safe driving behavior? That's this multi-agent prior here. So try to optimize that, but also try to optimize the probability of getting to your goal. So we've got like a probabilistic notion of success or goal completion. And that can be represented by having, say, Gaussian waypoints. So, you know, the closer you are to the waypoint, the more likely it is that you've succeeded. Usually when we give waypoints, we don't expect the car to get within a millimeter or a centimeter of the waypoint. We just, you know, want the car to get somewhere close to it. So, you know, we could have a Gaussian, this could be just a Gaussian kind of isometric Gaussian with a standard deviation of 1 meter, for example. If we're off by 30 meters, we're probably going in the wrong direction. But if we're within the meter, we've probably done the right thing. Yeah. Okay, so I think I probably spent a bit too much time on that. So I'll go very, I'll try to speed it up through deep bisimulation for control. So this is really how planning can help perception. Okay, so the first question is, are all percepts equally important when it comes to perception for autonomous driving? So here we've got a cartoon figure, like green fields, you know, over here in this image, we've maybe got a house and a cloud. And over here, we've got, you know, a tree and a road and some cars. And so is the car, is the road, is the house, is the cloud, are they all equally important to predict accurately and classify accurately? Okay, so I hope the answer that you're all thinking in your head is that they're not equally important. Things like the road and the car are probably going to be more important, but we don't necessarily know how much more important immediately, right? But one of the things that we were trying to do here was work out, can we develop a system for representation learning that can take both of these images here and say, oh, actually the important bits are similar. So these car positions are similar, and the way in which the road is shaped is also similar. But I don't really care so much about if there's a cloud in the sky or if there's a tree like far off the road or a house far off the road. So it would be interesting if we could come up with a latent space that can automatically understand that these two images are actually the same. And we should be taking the same action with respect to either of those images. We shouldn't be changing our actions because there's a cloud in the sky, for example. But if there's, say, a lack of a car or the road's facing a different direction now, it's going off to the left instead of the right, this is now a behaviorally different image as far as downstream control is concerned, right? So can we encode this image to a different area in latent space that we can then use to make predictions and develop controls for the vehicle? So, okay, so I'll hopefully wrap up in 3-4 minutes. Basically, learning representations for control with bisimulation is the paper. And we started off by kind of asking the questions like, or by making the observations that with generative modeling, there's been a lot of progress using sequential, VAEs and other things and GANs, and a lot of that can help learn control in these Majoku or DeepMind control or Atari tasks, and they can help you come up with representations that really kind of speed up reinforcement learning to learn these tasks very fast. But one of the interesting things about these environments is that there's not much visual distraction or noise in these environments. Usually if there's a change in the observational space, it's usually relevant to the task. So that is not always the case in the real world, right? So for real images, say with autonomous driving, most of the information is what I'd call junk information. It's not really a lot of the architectural details of the houses, the birds in the sky, the way in which a tree branches are particularly shaped. Like a lot of it is just information that we don't want to carry around. And so if we're using a reconstruction-based representation like a VAE, a variational autoencoder, it's going to try to represent everything, right? And that can be a problem when most of the information is junk information. And there's only a tiny bit that is actually the key bits that we actually want to kind of represent well and accurately. So we started asking, okay, so do these generative models, these VEs, do they start to degrade the more task irrelevant information we start introducing into these environments like Majoku and Atari? I mean, we only used Majoku, but I think in the interest of time, I might just skip over the math, but would be happy to answer questions afterwards over email. It's all there in the paper, but basically bisimulation metrics are really about coming up with distances for observation. So observation 1 and observation 2. And the way in which it's defined is a recursive relation where we say this distance is defined as, so worst possible case scenario here, so the max over all actions, the distance in possible rewards that we would get at the next time step, plus a discounting of the next distance, right? So if they're functionally equivalent, you can think no matter what actions I take, I'll get the same reward sequence if we unroll this recursive relationship. But if there is something in the scene that is very different, say like a wall that's next to us, then if we take an action that turns right and we crash into the wall, we will get a very different reward. And so this relation will then understand that, oh, this is a functionally different situation, and you do need to be mindful of things like the wall. But there's nothing that a bird in the sky, for example, could do that could change our reward. And so hopefully what we can do is then collapse different images that only differ, say, in terms of birds in the sky or clouds in the sky, to actually being the same, which is what this loss function does. But in the interest of time, I'll just skip over this bit and just talk about the different level of distractions we introduced for Majoku. So here is DeepMind control. So some different robots here. This is the typical setup. We then replace the background with kind of floating distractors. Importantly, this isn't random. They don't just pop up randomly, but they actually move. So sequential autoencoder capacity will be devoted to trying to predict where they'll go. It can predict it, and it will devote capacity to doing that. And then we also replace the background with natural imagery. So this is now much more complex. And what the model ended up doing was to learn correspondences like this. So here we can see with the natural background, we've got a robot that's in a very similar situation in all of these pairs, but the background is completely different, right? And so what's happened here is the bisimulation latents. This is a t-SNE of our representation. It's actually learned to pair these things. It's understood that these are the same state functionally. Whereas a VAE, it says, no, everything matters, the background as well as the robot, and these backgrounds are very different. So I'm going to encode these two completely different areas of the latent space because they are different. The colors here represent the values. And so because the bisimulation latents are based off the rewards, you get this nice consistent kind of color pattern here as you move around the latent space. Okay, so this is all very nice. We compared our models against a bunch of different things, including soft latent actor critic Slack here, which at least at the time was the arguably the kind of leader in these things, doing representation learning for kind of accelerated reinforcement learning in these situations. So so basically. So basically in the native DeepMind control, that would do really well. I think our method is in green here. When we start ramping up the complexity, so we've got the kind of floating orbs in the background, that's when all of these methods start to kind of come together a bit. They're all performing at the same amount, roughly. And then when we put in the natural videos, that's when these methods just, die. So these like reconstruction methods, they're trying to reconstruct everything, right? It's an incredibly hard task, and they will eventually do it. It just requires a lot of data to understand the complexity of how the background is shifting. So this is really the setting where, even though our method did, quite comparatively very poorly in the initial setting without distractions, with distractions, it's doing better. Yeah. So, okay. So basically we did this in Scala. We came up with a reward that is basically just highway progression and a collision penalty and a steering penalty. And then this is what it looked like. So we had the latent space where, if we sampled from this latent space to look at, that latent, what was the observation that generated that latent? Generally it's not you can't reverse the mapping, but we would just keep track of which observations generated which latents. And this is what it looks like. So up here, we've got an image, a dark image where we're next to a wall, and here we're next to a silver vehicle, and here we're next to the Scala Cola vans that we learned that Scala really enjoys populating their worlds with. So here, these are functionally the same. We've got basically there's just some object. We're driving down the highway, but there's some object to the right. And it doesn't matter if it's a wall or a car or a truck. It doesn't even matter the weather, right? So here we've got nice weather. Over here, we've got cloudy weather and more cloudy weather. They're all the same state as far as the bisimulation metrics are concerned. It's fine if you go straight forward. It's not fine if you turn right. Otherwise, yeah. And so basically, you're going to get the same reward stream in all of these cases. So then if we select cases down here, we've got a case where the car flipped over, and so it's looking at the wall. It's on its side. And so this is wall. Again, it doesn't matter what color the wall is or what the sky's weather is. Over here, we've just got open highway driving. Again, it doesn't matter what, if the sun's setting or if it's like overcast or something, or if there's shadows, it's all the same state. Yeah, so I think that's, sorry for running a little bit over time, but yeah, that is how planning can help perception. And yeah, any questions, please let me know.
Great, thank you, Rowan. That was very interesting. Yeah, let's see if we have any questions. I don't see any questions now in chat, so maybe I will ask just one question. Are you still working on this topic? Because I remember that this was your research work done at University of Berkeley. Are there some interesting open research problems or interesting research directions in this domain for people who would like to start working on it? Because it looks that it's quite original and interesting. So I believe that it might be interesting for some researchers.
Yeah, I think, yeah, so this is previous, this is, yeah, work at Berkeley. I haven't actually published anything at Toyota yet, so it's not, I haven't been able to talk about that. But I think, yeah, there was some interesting follow-up work by Castro and Bellemare and others on policy similarity embeddings or policy similarity metrics. It was also an ICLR paper that instead used action-based representations. So we based our representations on rewards, but I think there's a lot of interesting work that can be done, especially with imitation, if you look at action-based representations. So, if you've got some kind of demonstration or something like that. It doesn't necessarily have to be rewards that you use to group similar observations. It could be other functions of observations. It could be the actions themselves or a combination thereof. I think so. It's definitely something I'm still working on. I think there's a lot of ways to go from here. Like a lot of different kind of directions to go.
All right, great, thank you. I don't see more questions in our chat, and there's one question from Markus. In fact, have you looked into simpler distributions for the first method?
Using SimClear to basically differentiate, like as a.
So Markus, maybe Markus can clarify.
I can clarify. Yeah. Sorry, not SimClear, simpler distributions. Like you've been using flows, and flows are quite exciting right now. Have you used just mixture of Gaussians or anything else that can represent multimodality?
No, we didn't. But yeah, definitely you can achieve multimodality and often state-of-the-art kind of competition, results with mixtures of Gaussians. So we have not tried it. But I think the precog, that precog work, the conditioning on goals, that was really building off this paper called R2P2, which was using the autoregressive normalizing flows. One of the advantages of using that is that you don't have to choose the number of modes. And so theoretically, it can come up with as many modes as it needs to. In practice, it kind of just comes up with a small number. I think I think the other advantage is that the way in which it is structured with kind of factorized latent variables makes it very amenable to combining with planning, by planning through those latent variables. So possibly the same, I'd have to think about it, possibly the same thing could be done with Gaussian mixtures, where you plan through a set of latent variables to transform a prediction algorithm that uses that samples from those latent variables to a planning algorithm that then sets those latent variables. So that's a long answer to say I haven't tried it, but I'm sure something similar could work. Yep.
All right, perfect. Do we have any more questions? Yeah, I think that's all. Thank you very much, Rowan. That was really great and exciting. So thanks, and Markus, it's your turn. So Zoom is yours. Let's start sharing.
All right, let's see. Quick question: can you see those?
So it's loading. Yeah, can see it now.
We can see it. Mm-hmm.
Oh, okay, perfect. It doesn't show up on my end. I just see a big picture of you, Pavel. But I'll try to work through this. Overall, this is a little bit of an experiment right now. This is a talk that I'm usually giving in a somewhat academic setting, and I've tried to adapt it. Like I had the chance, first of all, thanks for the invitation, but now, given the broad audience, I had the chance to give a talk either very broadly about reinforcement learning or try to do something a little bit more nuanced and try to get away with like some insights in the bits of recent papers that we've written. And so now, while the title is Hindsight of Policy Options, Disentangling Abstractions in the Option Framework, we can, let's try this. We can try to simplify it. And I'll be talking about reinforcement learning, in particular in the context of data efficiency in the application in robotics and like how hierarchy affects data efficiency. Obviously now this is a talk including the work of many amazing collaborators at DeepMind, and I've tried to include some of them here. And I've started my timer, and I'll try to get through this as quick as possible. And whenever there are questions, please raise your hands. Like if it's something very general, then please just raise your hands directly, and I'll try to answer them as we go along, kind of. And I've tried to adapt this talk by essentially explaining every equation that you'll find with a little bit of a text box. So we'll make this as simple as possible. Overall, for this talk, I'll iterate through what is reinforcement learning, then kind of from reinforcement learning to supervised learning as like a way to simplify our optimization here, and then talk about two ways of including hierarchy in our optimization problem. All right, wonderful. So every talk about reinforcement learning in recent years has to start with like the obligatory slide about what is exciting about it. And while I dive into the details about math later on, this is what we should start with. When you've been recently kind of following the news, you will have seen great results in a lot of domains where we have like game-like structures. Imagine playing Go, playing Atari, playing StarCraft, like even something as complex as StarCraft by now can be solved to a large part at like superhuman performance via reinforcement learning. But for me personally, like the second row here is much more interesting. When we look into real-world applications, like things that cannot be exactly simulated, we look into optimizing the energy efficiency of data centers. We look into, in particular in my context now, in applications in robotics, and there are even people looking into reinforcement learning for autonomous driving. But as previously mentioned, there are some challenges in doing that. My presentation here will largely focus on robots who are somewhat stationary, robots who can also make mistakes, so that actually we can learn from these mistakes. But to start with, very quickly, since I don't have a broad overview of who actually is joining here, let's start with the idea of what is reinforcement learning. So if you now see this in the context of the kinds of machine learning that most people are kind of familiar with, if you look at like unsupervised learning and supervised learning, the main difference to reinforcement learning is that we're not giving a data set in the beginning. We're considering a system that can generate its own data set. So to go into detail, we have an agent, a kind of like the system that we designed, the system that we'll train also, that interacts with its environment, that performs actions, and receive some kind of observations of how the environment then changes. And that includes a reward. And the reward is the kind of thing that is something that is either given by the environment or something that is given by us as engineers that we design that defines what kind of behavior do we want to have. And now if we look forward, like the agent is kind of defined as a policy, like some kind of distribution for which we can sample. And in the most common case, and like let's say in our applications here, we also use a critic, which is a model that just says, like, if you have a state and an action, how good is that action? And given the agent's behavior, if we're in that state action pair, how much reward would we see in the future? And that's essentially it, like, how good is that? And the goal of reinforcement learning now looking forward is to train our agent to optimize some kind of objective. And the objective really is just to say, maximize our rewards that we see. And now to go back to one of the earlier slides, the top row and the bottom row were quite different. In the top row, we can get simulatable environments. Imagine things that we can exactly realize on our computers. Therefore, get massive amounts of very cheap data. Well, the second row, like we can derive simulations, but these simulations will be always inherently inaccurate. So however we want to address the second row in the real world or with simulators and then try to transfer, data in the real domain that we want to then apply in like remains limited and remains expensive. And with that, we directly come to the point of the main point of the talk. We'll look into ways to address this kind of data problem, and we look into ways to increase our data efficiency of our agents. In particular, I'll focus on training some kind of like modular, flexible, and hierarchical policies. And if we like look at the standard reinforcement learning setting in continuous control, when we want to model an agent that acts in a continuous action domain, we very often use Gaussian policies. And in that context, we just have a state. Based on that state, we will sample an action, and the environment will transition to a new state. If we look at the graphical model for something slightly more complex, then we look, for example, at a mixture policy, where we split the decision problem into two levels. We say, like, we first determine a high-level action, and based on that action, then we can determine a low-level action. And only this action will be performed in the environment. And I'll talk about the specific method for training these kind of policies. So what this gives us is this kind of like action abstraction from the based on this decomposition of the decision problem. And finally, when we look at hierarchical policies, what we can also do is we can not only abstract with respect to actions, but we can also introduce abstractions with respect to the temporal aspect of the problem. If we now look, for example, at option policies, in the context of what I'll be presenting about is hindsight of policy options here, then what we can do is also model the transition between options at consecutive time steps. So instead of like sampling high-level behaviors at every step, we can look into sampling high-level behaviors based on what was before, so we can continue with one, or based on the current step. And we enable the agent to be more consistent in that way. We want to use robust and data-efficient optimization, obviously, in particular because we want to look at robotics tasks. And if you want to be bold, we look at trying to solve them from pixels directly. And if the time suffices today, I'll try to also give like a broad overview of HRL and kind of like the insights with respect to our little contribution here. So first, let's start talking about optimizing just Gaussian policies. There are different ways of training our agents. What I've described before in the context of perceiving action, perceiving states and rewards and acting directly, you could consider that whenever you perceive a new state and whenever you perceive a new reward, you directly learn from it. However, if you want to be more efficient, we could also store this whole data and try to learn them from a kind of replay buffer. And we'll talk about that in most of the talk here. Essentially, in that context, what we look at is optimizing our agent by taking data from that replay buffer, sampling actions based on that data, evaluating these based on the critic, and we'll ignore the training of the critic in this talk based on time limitations. And based on these evaluated actions, we'll just update our policy. And the easiest way for me to describe this is to give you some visuals. If you look at the graph here, you'll see, let's imagine like a one-dimensional action space. We'll see the policy as a distribution in orange. We'll see some green samples that we've now just gathered. And we have a Q function that kind of, or our critic that says like how good each of these samples could be. We will evaluate them. And after we've evaluated them, we can just refit our distribution that represents our policy to these action samples that have now been weighted. And that's our whole update. If I would have the time, I would also discuss a couple of other potential policy updates, but I think given limitations here, we'll just leave it at that. Another way to just now look at this more on the basis of equations is we'll determine some weights based on samples of actions that we've gathered. And then what we'll do is actually supervise learning with our policy. So we just perform maximum likelihood on these weighted actions again. And the thing is that we've just seen is that we just need to be able to sample from our policies, and we just need to be able to like determine the probability of actions under these policies. That's everything we need for our optimization. And that's kind of the foundation of being able to train a huge kind of range of different distributions and classes of distributions here. Just quickly to give a spoiler again, why are we doing this? So now we found ourselves in the context of robotics, and some of the tasks that we're right now interested in are potentially in manipulation. So interaction with broad sets of objects, restructuring them, kind of like pick and place tasks, something that you would find in the end in logistics. And just, yeah, as said, like there's a quick spoiler here ahead. What we've been working before we started in this direction is like experiments that took us about a month, and that's a really bad iteration time. And with a couple of changes, including now using mixtures, we've gotten this down to a week, which is much more efficient for us right now. And to give you kind of like a block diagram, when we look at Gaussian policies in comparison to now mixtures, we can say either we have a network that just parameterizes your Gaussian, or we take a step further and we actually have networks that parameterize each of the different components of your mixture. So each of them is a Gaussian. And we have a network that parameterizes a categorical distribution. All of this together, it gives us the joint distribution over like the component that we're using and the individual action. And since I'll be skipping the optimization for that part, we can now just look at the results that we'll get here. We look at the multitask scenario. We look at something like reaching tasks, moving tasks, And we also have a box here with which we interact. So we can open it, put things inside, move things out of it again. And if we now train different kinds of policies, including like the flat policies that I mentioned before and our hierarchical extension, we can see that in the simple tasks, it actually doesn't matter what we train. Like the main complexity of the task lies somewhere else, and just changing the distribution will not help us here. However, if we look at more of the complex tasks, for example, now just getting everything here into that box, we get a significant advantage with respect to the overall time that our agents take here. We've run the same algorithms also on a real robot, and we see similar advantages. Sadly, in the context of real robotics, like resetting the environment automatically and interacting with boxes is really hard. So we stayed with a slightly simpler set of tasks here. So that just involves stacking as hardest tasks. And so they can see on the bottom right, within stacking, that this is still like a very significant benefit that we can gain here with hierarchical policies. And this is just a broad overview right now about the general tasks that our agents need to solve in this domain. Excuse me. In the next step, we will look into training options now, and just to follow the narrative that we've seen before from the block diagram, then we can see that if we have a Gaussian, we just need the parameterization for the Gaussian itself. For mixture, we extend this slightly by parameterizing the individual components and also the categorical. And in the last step now, what we're doing with options is really just changing the parameterization of the high level. Now, this is described here in a slightly simplified way, but essentially what we get with the graphical model that you see at the bottom is that the probability now for being in any of these options depends on the trajectory that we've passed before that. And there's a slightly simpler way to look at this, and this is now where it gets a little bit more towards the interesting side of the mathematical background. We can actually now determine the probability of being in each of these components in a trajectory by rolling out these trajectories and by determining kind of like the probability of being in one component based on where we were before. We have a kind of transition function here, but if we simplify this, the core of what it really means is just that we can determine the probability of being in one option based on the state that we're now in and based on the previous option. That is everything that we do. And if we now roll this out along a trajectory that we've just gotten from our replay buffer, we can do this like for every single state that we have here. And for every single state, we can apply some kind of reinforcement learning objective. And then since we're using deep learning as with most work recently, we'll just backpropagate. But so the interesting thing right now is that instead of backpropagating through one neural network, we can actually backpropagate through much more and optimize a bigger part of our overall like inference procedure here. If you want to see them that way, like a neural network is just a sequence of equations, really. And what we have here now, an inference procedure, is also just a sequence of equations. And as long as that's differentiable, we can actually, instead of just backpropagating through the current step in time, we can backpropagate until the beginning of the trajectory through the whole procedure that we've just rolled out. And we can do this really for every single time step that we've reached, and until we are back at the beginning. So let's see, we got a little bit of time, so I'll just broadly skim this. The high-level idea is that now that you've created this inference graph, which as of now is two-dimensional, you can play around with this kind of structure. And what you can actually do is you can turn this like two-dimensional object into something that has 3 dimensions. Now, with that third dimension, since you kind of control the creation of this graph, you can do something such as count the number of switches between different components. And with that now, the third dimension just automatically represents along a trajectory how many times have you switched your behaviors. And now, like we have an extended version of the transition function here, but we don't need to look into detail. And the thing now is that if we want to determine again the probability of being in one of those behaviors, we can just sum over all possible switches, just marginalize it out. But if we want to say we actually now, in addition to that, want to train a policy that is more consistent, that stays with one of these behaviors for a longer moment of time and kind of shape the behavior in that way, we can actually just marginalize over part of it, which is a very easy way for us to just use the existing structure in the algorithm and train something that behaves slightly differently and that behaves more consistently here. And now, so the tasks that we've been looking at for this algorithm sadly don't include real robots, because in the given situation, we did not have that much access to the real robots. But when we look at the results that we get in simulation as of now, then we can see that we can significantly accelerate based on just using mixture distributions in green in comparison to blue. But we can also, when we use options, accelerate even further. And this becomes more clear when we look at harder tasks, such as the stacking problem. Again, just as before, we see a couple of tasks from a multitask scenario here. And if we want to make this a little bit more interesting, we can also talk about the aspect of temporal consistency. So what I've described before is essentially a way to represent action abstraction with a mixture. What we've also seen is a way to represent temporal abstraction by just extending this towards the option model and just saying we have termination conditions, which we also learned. But what we additionally can do in the end now is optimize for temporal abstraction, as described last slide, 2 slides back. And if we do this for both domains, then we see on simpler environments that it doesn't matter a lot. And we also see that if we train from scratch, it has comparably little effect. But since we have modular policies, we can interact with it as engineers in a very modular way. So we can just reload a part of it. Imagine you've solved a couple of problems in the past, and these problems are related to what you want to do right now. So you just reload these low-level behaviors. You can also mix them from multiple experiments if you want to do so. And so these experiments are doing right now just that. We take a few previously trained low-level controllers, and we train a new high-level based on them. And when we do this, just as like a kind of sanity check, we look at the rate of switches right now between behaviors. And we can see in red that if we optimize for like limiting switches, then we can get much more temporally consistent behavior across both tasks. And the interesting thing is also that, particularly for the stacking domain right now, we see that if we reload temporally consistent behaviors, that kind of makes the exploration problem for the high-level controller easier. So you solve these problems, but you solve them by exploring a smaller space. And that is great because it just goes quicker. Let's see, I think I have a little bit of time, so I'm going to talk about this as well. So imagine you have all of those low-level behaviors, all of these like kind of, we don't control what they are, but they've been trained over like a broad range of tasks. So you get something like reaching, grasping, lifting, and like variations of these. And so if it's then easier for a high-level controller with these behaviors to solve a new task, and it's an easy task, why not replace that high-level controller with a human? Why not see what we can do when like controlling a system based on interacting with a reinforcement learning trained agent? And that's now exactly what we'll see here. I hope I'll be able to play that video. So essentially what we can do with this is now we can like fix these components and investigate what actually these models have learned. And this is what I'll be doing on the left here. And what we can also do, which is maybe more interesting in the long run, is that if you trained a reinforcement learning agent, if you trained a kind of like skill module that it can interact with, and you replace this high-level controller now by just like keyboard inputs, for example, you can try to solve a broad range of tasks with a much easier interface. Like imagine if I would be right now controlling all the different joints of this robot. It would be an incredibly hard task. If I now instead just control between a set of maybe like 10 options here, this is much easier. It's still something that needs exploration, but it gets us to a much more natural interaction with the system. And now looking, for example, in the future in continuous kind of behavior spaces will render this much more useful. All right, and since we have enough time, let me quickly iterate over where we're ending up right now. So in general, where we are is we have robust policy optimization, we have a modular and data efficient setting, and in particular, the modular has been underexplored. Because now when we have related tasks, we can very often reuse parts of behaviors. And when we want to see this more from a kind of, let's call it an engineering perspective, something like we really just want to make something work and we're less interested in making the math that complex, then we can develop much more solutions in just reusing previous behavior. And that is also one of the points right now under next that I would emphasize. In reinforcement learning, what we're doing very often is that we just start experiments from scratch. And as long as we're like working with simple domains as like the benchmark domains that are common right now, like OpenAI Gym, DeepMind Control Suite, and so on, that does not matter very much. But we're targeting more and more complex tasks, and our experiments taking longer and longer, from weeks to months. Being able to reuse previously extracted knowledge is incredibly important. And maybe to not only reuse it, but also to reuse it then as like a human operator to interact with that system. I think at that point, I'll be essentially running out of time. So thank you very much. There are a couple of references here if you want to look something up, and I'll be open to answer any questions.
All right, great. Thank you. Thank you very much, Markus. Yeah, are there any questions? I will have one question, actually, but first, let me also post a link to a short survey. So if our participants are interested, they can just fill in a survey to give us feedback about this event. Yeah, and my question is, so you said that you've run your experiments using a simulator because you didn't have access to real robots. So was the simulator somehow calibrated based on real data, or do you expect that the results using the real robots might be somehow different?
Yeah, so for the first experiment, for the first method that I've presented, we've performed experiments both in simulation and in the real world. Like if we're going back just a couple of slides here. So everything that we're seeing here, essentially, like we had some results in, and this is built on Mojoko essentially. We had results both in simulation and in the real world for very similar settings. And if I would have had enough time, I would have shown you also results for just like the pulse stacking for the simulation, and you get very similar results. So it's expected that it's quite similar. The main challenge that I see right now in like the context of manipulation tasks really is that contact simulation is really hard. And while our general, like the overall scheme, imagine like the ranking across approaches, usually generalizes between simulation and the real world, directly transferring approaches. Like imagine, I've been talking about reusing previously trained policies before. Imagine if you have trained a couple of options from simulation and want to use them in the real world. Like that's a much more challenging thing, in particular in like hard and complex contact tasks.
All right, great, thank you. Okay, I don't see more questions in our chat currently. So yeah, Markus, maybe if you have some extra information that you would like to share, then we still have just maybe 1-2 minutes if you want, and you can also wait for us.
Let's see. So what I did before is I reduced my set of slides drastically, but all that I could present right now would be additional details from the middle.
Okay. There is another question posted right now, so maybe I can answer, and I will ask and let you answer. So human in the loop, how is it possible to make policies understandable to human, that human can control them?
Very good question. Okay, I'll just scroll a little bit back and show the results again that we had here. So when we look at what we were doing here, it's loading a little bit slow, but what we're doing here is essentially in the first instance, we train an agent without any information about how you want to cluster behavior, how you want to shape that kind of skill space. Essentially, we have to interact with the system then to know what it actually does. If we provide additional shaping to the kind of skill space that you learn from the beginning, which obviously comes at additional costs, so that would include additional supervision that we as humans need to provide during training, then the later interaction will obviously be easier. It would be good in general to find like a common ground between the two. And we've been working in the past, like this was, I think, 2017, 2016. I was still at Oxford. We were working on a method that was using like weekly supervised learning in the context of imitation learning. And approaches like that kind of like minimize the effort for additional human labels, while kind of like maximizing the interpretability of the behavior that you get out of it. I think are a valuable direction.
Great, thank you. Okay, it looks we don't have more questions now. So yeah, Markus, if you would like to share some extra information, then we can still do that, but.
So I mean, the only thing that kind of like stands on its own that might be interesting to look at right now is that we've been looking at a couple of other scenarios here where so far what I've been showing is mostly in the manipulation domain. So let's imagine we can do the same things also in the context of locomotion. And if you look at locomotion domains, in particular across different embodiments, and apologies in advance because I haven't seen these slides in a while, you can look quite nicely into just additional metrics of what the agent actually learns. And this maybe connects nicely to Marek's question about like, how do we interpret the behaviors that come out of it? Because we need to interpret them so that we know what we can do with it. And we can look at, let me just focus on one particular metric. We can look at the context of information asymmetry. So what we've been doing is very, like, really simplified. Imagine the structure that I've described before, like with networks that parameterize your low-level behaviors and networks that parameterize the high-level behavior. If we provide all information to the low-level networks, then essentially you get to a point where really each of the individual Gaussians could potentially solve all the tasks that you give it, just because it has all the information. And now when we look at variations of that and just provide some of the information, not to the low-level networks, but provide it to the high level. And maybe if we would even go a step further and learn this, but this is not something that we do here just now, then we can look into like how these behaviors specialize when they don't have all the information. And I mean, the key point is that the less information you give to the low-level networks, the more they specialize, obviously, because they have to, because the high-level controller takes a bigger and bigger task. But yeah, I think this is kind of where I would leave it to stand. Like if you look at interpretability of behaviors and specialization of them, and in particular in the context of you as a human operator wanting to use this kind of like learned behavior later on as like something you want to control, then information asymmetry is a quite interesting direction to look into.
All right. Great. Thank you, Markus. Thank you once again. Thanks for a great lecture, answering the questions and the extra information. So I think that as for now we can wrap up. We can finish. So yeah, I would like to thank once again all our great speakers, Błażej, Rowan, and Markus. Thank to all of you for participating. If you are interested, please fill in our survey to give us a feedback. Our next Warsaw.ai meetup will be most likely in July, so stay tuned. And there will be information on our social media and discussion list. But for today, we can finish. So I'm just